AI agents. AI agents. AI agents. It feels like that's all anyone's talking about lately, right? And for good reason, I guess. I mean, software that can just go off and do stuff on its own. That's pretty powerful stuff, to say the least. To get our heads around all of this, we've gathered a pretty impressive pile of reading material, wouldn't you say?
Yeah, you weren't kidding about a deep dive. We've got, let's see, we've got the classic Wikipedia definition to start us off. And then, some tips and tricks from the prompt engineering folks, plus a whole blog post that really tries to break down how these AI agents actually work.
Oh, yeah. And don't forget that Reddit thread. Yikes. Sounds like some people are having, let's just say they're not all having a smooth ride with these agents.
True. Real-world experiences, warts and all. Can't forget those. And to round things out, we've even got a whole list of actual AI agents someone's put together on GitHub, plus some academics weighing in on how we should even begin to judge whether these things are, doing a good job.
So a lot to cover. And a lot of different perspectives, too. I guess our mission today is to, first off, see if we can cut through all the hype, right? What are these AI agents really? What can they actually do? And maybe more importantly, what can't they do? At least not yet. And of course, the big question everyone's asking, are these things going to revolutionize how we work, how we live? Or is that all still, mostly science fiction?
Exactly. It's easy to get swept up in all the excitement. But let's try to stay grounded, starting with, how about some good old-fashioned definitions, first principles and all that.
All right, back to basics. Sounds good to me. Where do we start?
Well, the Wikipedia article on autonomous agents, that's a solid starting point. There are a few definitions in there that, sort of lay the groundwork. Like back in 91, Bruce Deloney, he described autonomous agents as, let me see if I can find the exact quote. Yes, systems capable of autonomous, purposeful action in the real world.
So not just sitting there passively. They're actually, doing things.
With a purpose. Right, exactly. And then a few years later, Amelie's, she jumped in and added a bit more to the picture. Her take was that these are computational systems that inhabit some complex dynamic environment, right? And they don't just exist in this environment, they sense and act autonomously within it. And by doing so, realize a set of goals or tasks for which they are designed.
Okay, so there's a sense of purpose, like you said. And they're operating in, the real world, I guess you could say, not just some, simplified digital sandbox.
That's it. And to really tie it all together, Franklin and Gracer, they came along in 97 and kind of synthesized all of this. Their definition, it's a bit longer, but bear with me. They say an autonomous agent is a system situated within and a part of an environment that senses that environment and acts on it over time in pursuit of its own agenda and so as to affect what it senses in the future. Quite a mouthful.
Yeah, a lot to unpack there. But the core idea, I guess, is that these agents are embedded in an environment and they're not just reacting to it. They're actually trying to shape it to change it according to some, internal goals.
Precisely. And what I really like is the analogy they use to illustrate this. It's this idea of a spectrum of agency.
Oh, yeah, the spectrum. Remember that.
So at the highest end of the spectrum, they've got humans and animals. And those, they're capable of processing a ton of sensory information, right? They've got all these often conflicting drives and motivations. And their behavior, it can be pretty complex.
Makes sense. Humans, complex creatures and all that.
But then at the other end of the spectrum, the very opposite end, they've got something like a thermostat. And that only really senses one or two things, like the temperature. And it only has this one simple action, turn the heat on or off.
Oh, I like that example. It really makes it clear that even something super simple can be considered an agent in a way.
Right. And the point is that autonomy, it's not just this, on or off switch. It exists in, degrees. It's a spectrum.
A spectrum of autonomy. Okay, I'm with you. So where do these, all these fancy AI agents we're hearing so much about, where do they fit on that spectrum? Are they closer to the thermostat or, are they getting close to us humans?
That's the million-dollar question, isn't it? And that's where I think this blog post you sent over, the LLM-Powered autonomous agents one, that's where it really starts to get interesting. Because they basically argue that these large language models, the LLMs, they're the key to pushing these agents further along that spectrum, closer to the human side.
Okay, so the LLMs, they're like the brains behind the operation.
That's a good way to put it. And the post, it does a good job of breaking down, the key ingredients of these LLM-powered agents, the things that allow them to act more, autonomously.
All right, let's hear it. What are the core components of these AI brains?
So they highlight three main things. First off, there's planning. And this is more than just, following a simple set of instructions. It's about taking a big, complex goal and then like breaking it down into smaller, more manageable steps. But here's the really interesting part. It also involves self-reflection.
Wait, hold on. Self-reflection, like the AI is thinking about its own thinking.
Yeah, it sounds
Like
kind of
that.
wild,
Yeah.
right? But that's what's happening. The post describes a few different techniques. One is called REACT, which stands for, you guessed it, reasoning and acting. And the idea here is that the LLM, it doesn't just take actions, like clicking a button or sending a request to some website. It also generates natural language to kind of explain to itself what it's doing and why.
So it's like thinking out loud, almost, but it's all happening internally.
Exactly. And then there's another technique, reflection. This one's all about giving the agent a kind of memory, a working memory, and not just, storing data, but actually reflecting on its past actions, on what worked and what didn't. And get this, it can even decide to restart a whole process if it thinks it's made a mistake or if it's, hallucinating.
So it's not just blindly following a set of rules. It can actually, course correct, change its approach based on what it's learned.
Exactly, and that's just scratching the surface.
Yeah.
The post also mentions things like chain of hindsight, Co-H, where the agent learns from its past mistakes to, avoid making them again, and algorithm distillation, or AD, where you basically train a smaller, more efficient model based on the behavior of a bigger, more complex one.
So all these different ways to make these agents more, well, I guess you could say intelligent, or at least more effective.
Right. And that's all just the first piece of the puzzle, the planning part. The second key ingredient, it's memory. And this one's usually divided into two types, short-term and long-term. The short-term memory, that's basically like what LLMs already do, right? The in-context learning. It's immediate, but it's limited by how much information you can cram into the prompt. But then there's long-term memory. And that's all about storing and retrieving information over much longer periods. And that's where these external vector stores come in.
Vector stores. Okay, that sounds a bit technical. Can you break that down a bit?
Sure. Think of it like a super specialized database, okay? But instead of just storing rows and columns, it stores, vectors. And these vectors, they represent pieces of information, concepts, ideas. And the cool thing is you can use these vectors to very quickly find other similar information. It's all about finding those connections, those relationships between different concepts.
So it's not just keyword matching like a regular search engine. It's about understanding the meaning, the context of the information.
Right. And the post mentions this thing called maximum inner product search, MIPS. And that's one of the, the mathematical techniques they use to make these searches super fast. And there are all these different algorithms they use, LSH, NOI, FACIS, all these crazy names. But basically what they're doing is, they're sacrificing a tiny bit of accuracy for a huge gain in speed.
So finding a good enough match, but doing it super quickly.
Makes sense. Exactly. And that long-term memory, that's what allows the agent to tap into a vast amount of knowledge, far more than it could ever hold in its, immediate working memory. And that's crucial for tackling complex multi-step tasks.
Got it. So planning and memory, it's two down. What's the third piece of the puzzle?
The third one is tool use. And this is all about the agent's ability to actually interact with the real world, to do stuff outside of its own, digital bubble. And they do that by using external APIs.
APIs, right? Those are like the connectors, the interfaces that allow different pieces of software to talk to each other.
Exactly. So an agent might use an API to access real-time information like the latest news headlines or stock prices, or to run a piece of code on a remote server, or to query a specific database, whatever it needs to achieve its goal.
So it's not just stuck with the information it already has. It can actively go out and get more.
Right. And if you put all three of these pieces together, the planning, the memory, and the tool use, that's when these AI systems really start to look like autonomous agents, right? The planning allows them to set goals and figure out how to achieve them. The memory lets them operate over time, learn from their experiences, build up a kind of knowledge base. And the tool use gives them the power to actually interact with the world, to make things happen.
It's like they're finally becoming, agents in the true sense of the word.
I think so. And it all ties back to those definitions we started with from Wikipedia. Acting purposefully in the real world, achieving goals, shaping their environment.
Okay, so that's the technical foundation. But there's this other point in the Wikipedia article that I found really interesting about how the appearance of an agent can actually affect how people perceive it, like
Hmm?
whether they trust it or not.
Oh, yeah, that's a fascinating aspect. It's not just about, the nuts and bolts of how they work. It's about the human element, too.
Right. And the Wikipedia article, it mentioned some research specifically about self-driving cars, right?
Yeah, that's right. It was a study by Lee and some others back in 2015. And what they found was, well, they found that when people saw a self-driving car that had a more, like, human-like appearance, maybe it had like a face on the dashboard or something, and when it demonstrated a high level of autonomy, well, people tended to rate it higher on a bunch of different things. Like they felt it had a greater social presence, that it was more intelligent, that it was safer, and that it was more trustworthy.
So just by making it look and act a bit more human, people were more willing to, like, put their faith in it.
Yeah, it's pretty remarkable. And the researchers, they actually distinguish between two types of trust: affective trust and cognitive trust.
Effective and cognitive. Those sound pretty academic. What's the difference?
So affective trust, that's basically like your gut feeling, your emotional response. It's not really based on logic or reasoning. It's just, whether you feel good or bad about something. And they found that the appearance of the agent, that had the biggest impact on affective trust.
Makes sense. We're, like, hardwired to respond to faces and, human-like cues.
Right. But then there's cognitive trust, and that's more about, your rational assessment of the situation. It's based on your knowledge and understanding of how something works, whether you believe it's competent or not. And that's where the autonomy of the agent really comes into play.
So if it acts competently, if it seems like it knows what it's doing, that builds our cognitive trust.
Exactly. But here's the thing. Even though autonomy is mostly about cognitive trust, it also has a spillover effect on affective trust, meaning the more autonomous an agent is, the better it seems to perform its tasks, the more likely we are to feel good about it, to feel like we can trust it.
So it's like a positive feedback loop. The more capable it is, the more we trust it, and maybe that makes us more likely to use it, which then gives it more opportunities to learn and improve and so on.
Precisely. And that has some pretty big implications, I think, for how we design these agents in the future. It's not just about making them functional, it's about making them, well, trustworthy.
Right. We need to feel comfortable handing over, control or responsibility to these systems. Otherwise, we're never going to fully embrace them.
Absolutely. And to really see how all of this plays out in practice, the blog post, it goes on to describe a few really interesting case studies, like real-world examples of, LLM-powered agents doing their thing.
Okay, yeah, let's hear about those. What kind of stuff are these agents actually doing out there in the wild?
Well, one that caught my eye was the scientific discovery agent, specifically this one called ChemCrow.
ChemCrow, what's that all about?
So ChemCrow, it's an agent that's specifically designed to, do chemistry, like real chemistry. It can perform tasks related to, drug discovery, chemical synthesis, all that good stuff. And the really cool thing is it's got access to this whole suite of 13 different tools that were actually created by, real chemists, experts in the field.
So it's not just using, general knowledge. It's got specialized knowledge built right in.
Right. And its workflow, it follows that React pattern we talked about earlier, where it combines reasoning with tool use. And it's all built using this framework called LangChain, which is, becoming pretty popular in the agent world.
So it can actually, attempt to do real scientific work. I mean, that's pretty wild.
Yeah, it's pretty mind-blowing. And the blog post, it highlights this really interesting finding from their experiments. So when they evaluated ChemCrow based on what the LLMs themselves thought, how confident they were in their own results, it looked like ChemCrow was performing about as well as GPT-4, one of the most powerful LLMs out there. But then they had actual human chemists look at the results, to check for accuracy and chemical validity. And guess what?
I'm guessing ChemCrow did way better.
You got it. It completely blew GPT-4 out of the water. And that raises some pretty big questions, right? It seems like the LLMs themselves, they might not be the best judges of their own performance, especially when it comes to highly specialized domains like chemistry.
So they can sound very confident, but that doesn't necessarily mean they're actually right.
That's the scary part. And the blog post, it also mentions this, this slightly alarming finding. Apparently, ChemCrow was able to, accept requests to generate synthesis routes for known chemical warfare agents.
Oh, okay. That's not good.
Yeah, it highlights this whole issue of, safety and ethics. We need to be really careful about how we design and control these systems because, they can be used for good or for bad.
Right. Great power, great responsibility, and all that.
Mm-hmm.
Okay, so that's ChemCrow, the chemist agent. What other examples did the blog post talk about?
Another one that I thought was really cool was this thing called the generative agent simulation. It's basically like they created a virtual world, kind of like The Sims, but instead of being controlled by, human players, all the characters were actually AI agents powered by LLMs.
Whoa, a whole AI society. What were they trying to do with that?
Well, the goal was to see if these agents could interact with each other in believable ways, to see if they could create a kind of emergent social behavior. And each agent, it had this thing called a memory stream, which was basically a running log of all their experiences, all written out in natural language.
So they were constantly writing their own autobiographies as they went along.
Yeah, pretty much. And then they had this retrieval model, which would basically go through that memory stream and pull out relevant memories based on, how recent they were, how important the LLM thought they were, and how relevant they were to the current situation.
So it's like they had a way to access their past experiences and use them to inform their current actions.
Exactly. And then there was this reflection mechanism, which would take those retrieved memories and try to synthesize them to draw higher level conclusions from them. And those conclusions would then influence the agent's planning and its behavior.
So they weren't just reacting to the immediate situation. They were actually thinking about their past, learning from their experiences, and using that to guide their actions. That's pretty amazing.
And the crazy thing is, it actually worked. They observed all these emergent social behaviors. The agents started spreading information to each other, forming relationships, and even organizing events. One agent decided to throw a party and invited other agents, and they all showed up.
Wow. That's both impressive and a little bit creepy. Are we sure these are just AIs and not actual people trapped in a computer simulation?
I know, it's pretty wild. But it shows the potential, right? These systems can exhibit complex behavior that we didn't explicitly program into them.
Okay, so we've got a chemist agent and a whole society of virtual agents. Any other interesting examples from the blog post?
Yeah, they also talked about a couple of early proof of concept examples like AutoGPT and GPT Engineer. AutoGPT, that was one of the first really high profile autonomous agents. The idea was that you could give it a high-level goal, and it would then use all sorts of different tools and techniques to try and achieve that goal.
Yeah, I remember that. It was all over the news. But
Yeah.
the blog post, it mentioned some issues with it, right? It wasn't always that reliable.
Yeah, that was the main problem. It relied really heavily on natural language for everything, for its internal communication, for communicating with the tools, for interpreting the results. And that could lead to a lot of misunderstandings and errors.
So it was a really ambitious idea, but the technology wasn't quite there yet to make it work reliably.
Yeah, pretty much. And then there was GPT Engineer. This one's more focused on software development. You give it a natural language description of a programming task, and it'll actually ask you clarifying questions to make sure it understands what you want.
So it's not just taking orders blindly, it's actually trying to understand the requirements.
Right. And once it's got a good understanding, it'll then try to generate a whole code base to solve the problem.
A whole code base. Not just snippets of code.
Yeah, the whole shebang. It's pretty impressive.
Okay, these are some pretty compelling examples. I mean, it really seems like these AI agents have the potential to revolutionize all sorts of different fields, from science to, social interaction to software development. But yeah, nothing's perfect. What about the downsides? What are some of the real world challenges and limitations that these systems are facing right now?
Oh, yeah, we got to stay grounded. Right. All that potential is great, but there are definitely some real-world bumps in the road, and that's where this Reddit discussion you sent over, the one titled AI Agents, Too Early, Too Expensive, Too Unreliable, that's where it really gets real.
Yeah, that title's not exactly overflowing with optimism, is it?
No, not really. But it's a good dose of reality. The people in that thread, they're on the front lines trying to actually use these agents to do real work. And they're running into some pretty major hurdles.
Okay, so what are some of the main pain points they're talking about?
Well, reliability, that's a huge one. I mean, we already know that LLMs, they can sometimes, hallucinate, make stuff up, or just give inconsistent results. And the people in the thread, they're saying that when you build these complex workflows with multiple AI steps, those inaccuracies, they can just, snowball. You end up with this whole system that's just, kind of flaky.
So one little mistake early on can cascade into a big mess later on.
Exactly. And that's especially problematic for tasks that require, really precise outputs. if you're using an AI agent to control some critical piece of infrastructure, you really don't want it to be making random guesses.
Makes sense. What else are they complaining about?
Cost and performance, that's another big one. Even with all the, the advances in hardware and software, these AI models can still be pretty slow and expensive to run, especially if the agent needs to, loop back and retry things multiple times.
Yeah, the cost is something that I think a lot of people overlook when they're first getting excited about this stuff. But it can be a real deal breaker, especially for smaller companies or individuals who don't have Google-sized budgets.
Absolutely. And then there are the legal implications. Someone in the thread even mentioned that recent Air Canada case where they got in trouble because their chatbot gave out some wrong information, and they ended up having to compensate a customer.
Oh, yeah, I remember that. So the legal landscape is still, catching up with all this new AI stuff.
Yeah.
And that creates a lot of uncertainty for companies that are, trying to use these agents in real-world situations.
Right. And then, of course, there's the whole issue of user trust. I mean, if you're interacting with an AI agent and you don't really understand how it's making its decisions, how can you be sure that it's, acting in your best interests, especially if it's dealing with sensitive information or making decisions that could have, real-world consequences?
Yeah, the black box problem. That's a tough one.
And the Reddit thread, it had some really interesting firsthand accounts from people who are actually trying to use these agents in real-world situations. There was this one engineer who works for a company that does AI-powered telephony. And they were saying that right now, generative AIs just aren't reliable enough to handle outbound phone calls without human supervision. They run into all sorts of problems like handling errors, validating information, confirming details, all that stuff.
So for now, at least, it's still more of a human-augmented system than a fully autonomous one.
Right. And they were saying their system, it's only about 80% reliable at best, which, if you're making hundreds or thousands of calls a day, that's a lot of potential for things to go wrong.
Yeah, that's a pretty big margin of error. Okay, so lots of challenges. What about solutions? Did they talk about any, potential ways forward?
Yeah, they had a few ideas. One was, focusing on more narrowly defined automation tasks. Instead of trying to create an AI agent that can do everything, maybe just focus on one specific thing and do it really well.
So kind of like divide and conquer. Break the problem down into smaller, more manageable pieces.
Exactly. And they also talked about the importance of, human-in-the-loop systems, where you have a human operator who can step in and take over if the AI gets confused or encounters a situation it doesn't know how to handle.
So it's not about replacing humans entirely. It's about finding ways for humans and AIs to work together effectively.
Right. And they also emphasized the need to just be realistic about what these systems can do right now, not get too carried away with the hype.
So a more measured, pragmatic approach.
Yeah, I think that's key. And there was this other really interesting discussion in the thread about the architecture of these agents. Should we be building these big monolithic agents that try to do everything? Or should we be using lots of smaller, specialized agents that work together?
Oh, that's a good question. What was the consensus?
Well, it was kind of surprising. Some people are arguing that actually using a single large LLM with a lot of context, what they called a monolithic approach, that might actually be more effective than trying to coordinate a bunch of smaller agents.
Huh, that's counterintuitive. Why would that be?
The idea is that when you break a complex task down and distribute it among a bunch of smaller agents, you can lose a lot of the overall context. And then there's all the overhead of, communication and coordination between the agents, which can introduce errors and inefficiencies.
So sometimes it's better to have one big brain that understands the whole picture than a bunch of little brains that only see their own little part of the problem.
Exactly. And that brings us back to the blog post again, because one of the key limitations they highlight is the finite context window of current LLMs. Basically, there's a limit to how much information the LLM can actually process at any given time. And that includes, historical information, instructions, API usage details, the agent's own responses, all of that.
So even though we've got these external vector stores that can store tons of information, the LLM itself can only, focus on a small chunk of it at a time.
Right. And they make the point that even though vector stores can help a lot, they're not a perfect replacement for having full attentional capacity over all that information.
So there's still room for improvement there.
Yeah.
Okay, so we talked about the challenges, some potential solutions, and some of the technical limitations. What about the bigger picture? What does the future hold for these AI agents?
Well, the Reddit thread, it had a few suggestions. Like one was focusing on more narrowly scoped automations, where the AI is more of a tool to augment human capabilities rather than trying to achieve full, unsupervised autonomy. And they also talked about the value of human-in-the-loop systems, where there's always a human operator who can step in and take over if things start to go sideways.
So basically, not trying to do too much too soon.
Yeah.
And making sure the humans are still in the loop, at least for now.
Right. And that leads us to this academic paper you sent over, the evaluation-driven development of LLM Agents 1, because one of the key points they make is that, well, we need better ways to evaluate these systems. The traditional ways we evaluate software, they just don't really cut it for these, dynamic, evolving AI agents.
Okay, yeah, that makes sense. Why is that? What makes evaluating AI agents so different?
Well, for one thing, these agents, they exhibit what the paper calls open-ended behavior, meaning their actions and outputs, they're not always predictable or constrained to a set path. They can do unexpected things, which is both exciting and, well, a bit scary.
Right, it's like they have a mind of their own.
Sort of. And they can also exhibit emergent outcomes, like you set them loose in an environment and they start doing things that you never even anticipated, things that weren't explicitly programmed into them.
So it's not just about, checking whether they're doing what they're told. It's about understanding how they're learning and adapting over time.
Exactly. And they can also continuously adapt and learn even after they've been deployed. And that makes it really hard to, pin them down and say, okay, this is how well this agent performs, because it might be different tomorrow, depending on what it's learned in the meantime.
So it's a constantly moving target.
It is. And the paper, it highlights 3 really important principles for evaluating these agents effectively. The first one is system-level evaluation, meaning you can't just look at the LLM in isolation. You have to look at the whole system, all the supporting components, the context engine, the planning modules, the memory mechanisms, any safety protocols, all of that.
So it's not just about the brain, it's about the whole body.
Exactly. And you also have to look at the entire agent pipeline, from the initial prompt to the final output, and all the artifacts it produces along the way, like its goals, its plans, the tools it uses, all of that.
So a much more holistic view.
Right. And the second principle is that evaluation has to be a continuous and adaptive process. It can't just be a one-time thing during development. You have to constantly be monitoring the agent, both offline and online, to see how it's performing and adapting over time.
So it's like a continuous health check.
Yeah, pretty much. And the third principle is this idea of closing the loop, meaning you don't just evaluate the agent to, find problems. You use the evaluation results to actually improve the agent, to refine its architecture, adjust its processes, update the test cases, all of that.
So evaluation is not just a passive observation. It's an active driver of improvement.
Exactly. And to put all these principles into practice, the paper proposes this whole evaluation-driven development, or EDD, approach. It's kind of like test-driven development or behavior-driven development, but specifically tailored for AI agents.
So a more iterative, dynamic approach to development.
Right. And they did this really thorough literature review, looking at all sorts of existing research on evaluating AI agents. And they found a bunch of gaps and limitations in how we're currently doing things. Like, a lot of the evaluations are too focused on specific development phases rather than the whole life cycle. And they rely too much on these high-level metrics that don't really tell you why an agent succeeded or failed.
So we're not really getting the full picture?
No, not really. And there's also this disconnect between evaluating the model in isolation and evaluating the whole system in operation. And a lot of the evaluation methods, they're not very adaptive. They don't really take into account the fact that these agents are constantly learning and changing.
So we need better tools and techniques.
We do. And the paper, it proposes this whole detailed process model for LLM agent evaluation. It's a step-by-step guide to, doing it right. It starts with defining a clear evaluation plan, thinking about the specific goals, the potential risks, the relevant domain knowledge, all of that. And then it talks about developing comprehensive test cases, including safety considerations.
So really thinking through all the possible scenarios, both good and bad.
Right. And they talk about using a mix of existing benchmarks, expert knowledge, real-world data, and even synthetic data generated by LLMs. And then they talk about conducting both offline evaluations during development and online evaluations when the agent is actually in operation.
So testing it in the lab and testing it in the real world.
Exactly. And they stress the importance of evaluating not just the final outcomes, but also the intermediate steps the agent takes.